So another very popular pseudo-relevance feedback algorithm is called relevance-based language model, which was proposed in 2001, more than 20 years ago. But still, it is a very strong baseline that are used as a state of the art still in today's information retrieval research as well. So in this paper, what the authors did was they assumed that there is a latent relevance model. You can consider this as a simple PDF, probability density function, which is generating the set of relevant documents as well as it is generating the query. So for every query, we can consider, for every query submitted to a system, we can consider that there will be a latent relevance model from which the query has been generated and from which the relevant document for this query can also be generated. And this R is basically a probability density function. So the easiest way to actually estimate this R is based on this and this. This is known. This is the query that the user is submitting to the system. And what is this? This set of basically this is basically set of rel docs, isn't it? Now, in case they are marked like the true relevance feedback scenario, we can simply use this information and this information in order to estimate this probability density function. But in case this kind of a training data is absent, that is, in case there is no level of this relevant document known, again, we can perform an initial retrieval with the query. After performing the initial retrieval, we can consider the set of say top M document as basically this pseudo relevant document here. So based on this and this R is estimated. Again, I'm repeating, R is a probability density function from which the set of relevant documents are being generated, from which the query is also being generated. But we don't know which are these documents. The task of information retrieval is to select these documents, isn't it? We don't know this. Now, here, what we'll be doing is, after performing an initial retrieval with the query, we will be selecting a sort of top 10 or top M in general documents as pseudo-relevant, and we'll be considering them in order to estimate this R. Now, where we are considering this as the pseudo-relevant document set, the only absolute evidence of this R is the query. That is, we can definitely say that this query, that is this say Q1, Q2, Q3 are being generated from this R, from this relevance model, from this probability density function. Now, the task is basically to estimate this R, this latent relevance model, and based on which we'll be basically performing the query expansion, and hopefully we'll be improving the performance. But first we need to estimate this R, and based on which we'll be selecting a set of potentially good expansion terms. And based on this R, what we'll be doing is we'll be estimating the weight or the probability of individual words that are basically present in this R. Remember, as I have told you, this R is basically a probability density function. If we consider a normal distribution, some terms will be having some weight. So basically, by y-axis, we are plotting the probability. By the x-axis, we are basically plotting the weight, plotting basically the words. Now, this individual words, this individual weight of the individual words is what we basically will be estimating in order to estimate this R. Now, as we have told you, as it is evident that this Q is the only absolute evidence, we'll be estimating this PWR, that is the probability of generation of a word from this relevance model. We'll be estimating them on the basis of PW given Q. Why? Because we know Q is definitely coming from R. How we'll be estimating that? We'll be discussing now. So we'll be start the discussion with the basic probability ranking principle that we have discussed while discussing the probabilistic retrieval models. So suppose we have an accurate R, and basically we want to rank a set of documents to be presented to the user based on this R for a given query Q. Now, a way of basically ranking these documents D, which are belonging into this R, is basically based on their odds ratio. So the odds ratio is probability of D given R divided by probability of D given NR or N. That is how likely the same document will be selected from the relevance set divided by how likely the same document will be selected from the non-relevance set. So there are two sets. This is say R, this is say NR or N. How likely that a document under consideration, which will be ranking, will be scoring, is basically selected from this and selected from this. This can be estimated based on the odds ratio. And if we make a common word independence assumption, that is that words are independent from each other to be occurring in the document, we can estimate or we can approximate these odds based on the individual words in that document. So probability of D given R, in that case will be, so let's say D, that is the document, is containing say different words, say W1, W2 up to say WM. Okay. Now probability of D given R, that means what is the probability that I'll be generating D from R. Now if we consider the word independence assumption, that is individual words are occurring without anyone's dependence, that is all the words are occurring independently from each other, we can consider this as basically probability of W1, W2 up to WM given R, isn't it? So again, considering the word independence assumption, this is basically probability of W1 given R, probability of W2 given R into up to probability of Wm given R, which is basically simply we can write product over all W in D, probability of W given R. Similarly, the denominator, what is the probability of generating the document from the non-relevant set, can be approximated by the product of all W given n, oh sorry, given d, again here it is d, probability of w given n. So this probability rank, I mean based on probability ranking principle, if we want to score the document based on their odds, we can perform basically this computation considering the word independence assumption. Now here we'll be concentrating only on the numerator, that is, what is the probability that the word is generated from a relevance set. As we have discussed already, this is very problematic. I mean, estimating this is very problematic because n can be multi-topical, and definitely n will be multi-topical. But given a query, R is expected to be containing basically a single topic. That's why we can assume that there is only one probability density function that is underlying this R. And this probability density function is basically formed with the individual words, and we are basically estimating that weight of the individual words in this probability density function. So this probability W given R, as we have discussed, the only absolute evidence of R is Q. We know that Q is definitely generated from the R. So this probability of W given R can be approximated again with this probability of W comma Q divided by WQ, where this is basically the joint probability of observing an individual word along with the query. This is the joint probability divided by this is the query prior. Again, I'm taking one step backward again just to give you the overall picture again. So this R is basically set of documents, isn't it? Set of document, expected set of relevant documents, right? Set of rel docs. But here R is also considered as a single probability density function, where the words are basically the points in this PDF, and the words are basically coming from this relevant documents. In another way, we can consider this R to be a set of PDFs which are similar, because all the relevant documents are expected to be similar. So based on that, we'll be basically considering for individual document there will be a PDF, but all the PDFs are expected to be same, not exactly same, but expected to be similar. So here again the R will be the set of words, although we are considering it as a set of relevant documents. Here, considering this, we are considering R as the set of words present in this set of relevant documents. This is very vital to understand. Although R is a set of relevant documents, here considering this PDF as a single PDF, R is basically a set of words from this set of relevant documents. Now, considering this query prior, as the task is to score the documents, so basically PQ will be same for all the documents, so we can simply ignore this, and what we'll be ending up with is basically PW comma Q, which is basically the joint probability of observing W together with the query Q. So let's consider this scenario. Given a query, say containing K terms, and M is basically a set of initially retrieved document, which we'll be considering as pseudo-relevant document. We assume that if we sample individual words from this pseudo-relevant document, this initially retrieved document, after performing K drawing of word, the individual, if we perform K individual ball drawing or query, basically turn drawing, we'll be observing these terms for the k number of draw from the pseudo-relevant document, and the k plus 1th as a k plus 1th term will be basically the word that is under here under consideration. Okay. So again, considering this is basically, this is IID sampling, independent and identically distributed sampling. That is, there is no dependency between the drawing of an individual word from the urn, from the sample, from the basically the population. So what we are doing is, we are given this query, we know, again, one step backward, we know there is an R which is generating this k queries, k query terms. Okay, and from there we are performing, say, k number of times we are drawing balls, drawing words. The first k draw is actually giving us this k number of query terms, and then the k plus 1th, at the k plus 1th ball drawing, how probable that we'll be observing this W. So this can be, so M is here is basically the set of pseudo-relevant document PRD that we are considering, the top M after performing the initial retrieval. Note that this is after performing the initial retrieval. So if we consider that IID sampling scenario and this ball drawing scenario, that after performing the k retrieval, k ball drawing, we are observing the Wth word at the k plus 1th drawing. So it can be actually approximated, this joint probability. This joint probability can be estimated using this summation over all document in the PRD. How likely that document is retrieved? This is basically prior of the document, and from that document, how likely that if we perform a ball drawing or word drawing, how likely that we'll be observing the query terms together with the word. Basically, considering one urn, one document, we are performing k plus 1 sampling. And at the first k sampling, let's consider we have observed the individual query terms. And at the k plus 1th drawing, we have observed the W. So how likely that we'll be observing this? So based on this, we can approximate the joint probability of the word together with the query. Now, how we are going to approximate this probability of W, Q given D? This is basically, as we are again considering this word independence assumption. So this is basically, this can be written as this can be written as probability of W, Q1, Q2, Q3, up to Qk given D. As they are independent from each other, it is basically probability of W given D into probability of Q1 given D into probability of Q2 given D up to probability of Qk given D, and this can be clubbed together as this. Okay. So again, if we put this here, what we'll be getting is probability of W, Q, the joint probability of observing the word from the query together with the query words, is basically summation over all documents in the pseudo-relevant document set, probability of D, that is the prior probability of selecting that document, into what is the likelihood that that word under consideration is selected from that document, into this is basically approximately, this is the score of document D for the query Q. This is approximately the score. Now, as we have started with, we discussed that we'll be approximating R by Q. Based on this, we'll be basically approximating the generation probability of the individual words from R. Now here, this is basically the maximum likelihood estimate of Q, the query in D. This is, as I have discussed, this is approximately language model based retrieval score. This part is basically the maximum likelihood estimate of the word in document D, and PD is the prior probability of selection of that document. Now again, I'm taking one step backward. Our target is to estimate this R, the probability density function associated with R. Now this R is, although we started with this R as a set of documents, here considering this PDF, this is basically the individual words, isn't it? Which is basically forming this R. Here we are basically considering these W's as the individual component of this PDF. Any question up to this? I think I'll not be able to finish whatever we have planned today, like the writing the algorithm, but definitely the discussion is a must, a very important one. So we should be concentrating, investing some time in this. So any question up to this? So let me again just recap you. So R is, we started with, so M is basically the set of relevant documents. So sometimes we are referring to it as R as well, but here from the PDF's point of view, R is basically the union of all the words belonging to DI, where I equals to 1 to M. Basically all the words in this initial pseudo-relevant document. This is basically the union of all these words. Now, practically, or ideally, this R should be containing only those terms which are occurring in the true relevant document, isn't it? Here, this is pseudo-relevant document, isn't it? Set of pseudo-relevant documents. Now, here, we are, of course, you can understand that there will be so many terms which are not actually belonging into the actual R. So let me write it in this way. So this R, this is the pseudo R, let's call it R prime. And let's call R as the actual relevance set. It is basically the union of all the words belonging to the rel docs, the actual rel docs. Here in this R prime, which is basically the relevance set based on this PDF. So R prime is based on, not PDF, sorry, PRD, pseudo-relevant document, and R is basically based on the true relevance feedback, TRD, true relevant document. As true relevant document is hard to find because that's what the retrieval model is expected to be doing, to select a set of relevant documents. So this is not actually feasible to get. What we do is we perform an initial retrieval with the initial query. We select the top M number of documents as pseudo-relevant, and based on the terms in that pseudo-relevant document set, we are approximating this R prime, which is an approximation of R, and expected R prime and R will be close. So how to measure their closeness? A very basic way of approximating their closeness, if we have these two, is by using their KLD, say. So if we perform the KL divergence, it is expected to be very close to 0. And if the initial retrieval is good, in that case, it will be very close to 0. Very close to 0. Any question up to this? All right. So there is actually a limitation or a drawback of this relevance model. So this is called, this is known as this is referred to as with many names. One of them is called RLM, relevance based language model. Some call it RBLM. The most mathematical way of defining this is called RM1. Why RM1? So basically, this is, this is the first model that was presented by this Lavrenko Croft paper in SIGIR 2001. There was another method which is, rather than approximating this P W given Q using IID, in that other model they used a conditional sampling method, and that conditional sampling method is called RM2, relevance model 2. So this is, this is known to be working better than RM2, so that's why we'll be concentrating on RM1 only. So just to recap things up, here, based on the RM1 model, probability of a word given the relevance model is approximated by this formula. Say if I'm using the same notation here, D belongs to M. This is the set of pseudo-relevant document. Probability of D into probability of W given D into product over all query terms, probability of the query term given the document. Note that our ultimate target is to score a document, but here we are actually scoring a term. So based on this term scoring, what we'll be basically doing is we'll be basically selecting a set of terms as potential expansion term, EXP term. Our ultimate target is to score a document. So after performing an initial retrieval with Q, we are considering the top M document as pseudo-relevant, right? And then based on those pseudo-relevant document, so we are computing this. So what is the population of W? W is what? So basically we will be computing this value for all W belonging to M. Here M is basically, I should mention, for all W belonging to each DI, where I equals to 1 to M. So I hope you can now understand. So let's say after performing the initial retrieval, we select, say, top 20 document as PRD. Then this PW given R, this computation is performed for all words in the above 20 pseudo-relevant document. Compute PW given R. Okay. All right. So there is one limitation of this model, which is it is not actually providing any extra weight to the query terms. Remember that from R, this is basically some PRDs generated, and also this Q is generated, but this is an absolute evidence. We definitely know that this Q is generated from R, but there are the cases that there will be multiple non-relevant documents in this PRD, but still the query terms, that the terms which are occurring in this queue is not given any priority. So for all the words in the above 20 or above M number of PRD is basically being computed for their PW given R. The query word should be given higher weights. So in this, I mean, in order to address this model of address this problem or drawback of RLM or RM1, there is a model proposed in 2004 called RM3, which is basically a linear interpolation of PW given R, which is this, plus one linear interpolation between W given R and W given Q. So what is the probability that the word is being generated from the relevance model, and what is the probability that the word is actually a query term? This is basically a linear interpolation, linear combination between these two. So here PW given R is basically RM1 model, and this is basically the MLE of the word given the query. Now note that here I am mentioning I have actually excluded the PD here, which is the prior probability of selection of that document. Practically, without any prior probability information with us, we usually consider it as uniform. That's why here I have excluded that. So in total, RM1 formula is this. RM1 formula is this, excluding this PD. So here what we are doing is we are computing alpha is a linear interpolation parameter, which is basically will be between 0 and 1. Putting a 0 value means we are not actually considering the word generation from this relevance model. We are only considering the MLE from the query. And if we put a value of 1 here, we are not actually considering any special weight to the query at all. So this is basically cut. So we are only considering this factor. Now, why is it RM3? Because it is basically the mixture model with RM1. There is also an RM4, which is basically the mixture model, mixed model of RM2 with Q or Q model. So the summary of this RM3 is will be given a set of documents, of course the corpora, it will be corpus, set of documents, and a query containing say n terms here or k terms. We will be first performing an initial retrieval using language model or any other retrieval model. Then we'll be considering all terms in the top M retrieved document in the first phase retrieval as the pseudo-relevant document. and all those terms will be considered as the potential expansion term ET. Then we'll be computing this P prime WR, W given R, for all these terms, for each terms in this ET, based on this formula. Sorry, it will be only PW given R, because this is, we are only considering RM1 here. RM3 will be computed later on. So calculate RM1 weight for each of the words in ET following this formula. Then consider n number of terms which are having this highest weight as the final expansion term. Initially this might be containing say 1000 or maybe 2000 terms. For each of these 2000 terms, we'll be computing this PW given R, and we'll be sorting them based on this weight, and we'll be selecting the top words as the final expansion terms, and we'll be basically here we're considering top n terms as the final expansion words. And finally we'll be computing the linear interpolation here with the alpha parameter, interpolating with the query likelihood model.